Welcome to my talk titled Stochastic Optimal Control Methods for Optimal Water Management of Irrigation System. I am Effah Nyarko, and this is an ongoing work on my PhD supervised by Professor Ralph Bundelich, Professor Olivier Pamen, and Professor Nicole Boyle. Water is a scarce resource in the semi-arid regions, typically for crop farming. Artificial method like irrigation is used in mitigating this problem. However, the challenge is to find a smart water management which on one hand provides enough water to the farmland, allows for good growth of the crops, and on the other hand ensure availability of water over the whole dry season, such that the risk of ruin by drying out is kept small. Also, the new phenomenon of increasing variability of the duration of the dry season is another challenge feature in an irrigation management. Now consider a reservoir. Example is a micro dam with the bottom open. The reservoir typically is filled during the rainy season such that it can provide water during the dry season. An external inflow such as lakes, rivers, or underground water flows into the reservoir. The controller of the irrigation system can release water from the reservoir to the command area using an electric pump. But below the minimum level R underline, water is not possible to be released from the reservoir. The command area is described by growth yield and soil moisture. The latter is the content of water in the soil for crop production. The inflow of water from the reservoir increases the soil moisture, whereas evapotranspiration decreases it. Evapotranspiration is the combination of transpiration of water from the soil to the crops for growth and evaporation. On the other hand, growth yield quantifies the yield arising from crop growth through the utilization of soil moisture. Excess or less soil moisture leads to less yield via poor crop growth. Moreover, we assume that commodities from the command area is instantaneously available on the market at a market price. The market price is driven by an exogenous demand and supply quantity. In general, weather and environmental conditions such as precipitation generates uncertainty in the irrigation system. Further details of the slides is available using the link below. The challenge presented above is mathematically formulated as a continuous time stochastic optimal control problem. The state process X is defined on a filtered probability space with filtration generated by a 5-dimensional Brownian motion and controlled by U, where theta m of t gt is the evapotranspiration, beta t is the seasonality function for the external inflow, theta g of mt and gamma gt measures the impact of soil moisture and crop growth on yield. Alpha p and alpha z are the mean reversion rate, with dt exogenously given by the demand and supply on the market. The control process U is the flow rate of water from the reservoir to the command area. Water can only be supplied if the reservoir is above the minimum and the soil moisture is below the maximum, and it takes values from K curly bar. The admissible control curly AC is the set of all control processes that are adapted to the filtration, satisfying the control constraint with the decision rule U tilde, which defines the Markov control for t belonging to the interval 0 and the terminal time t. Furthermore, the runtime time tau m is the first time the soil moisture is out of the range of curly ms. Lack of inflow of water from the reservoir does not necessarily imply ruin. We assume that the seasonal time tau s has a known distribution and it is independent of all random variables. Hence, we define the overall stopping time tau. The aim of the controller is to find a control U that maximizes the expected discounted aggregate profit described by J. The current optimization problem is more complex and does not pose a closed-form solution due to the control constraints and the stopping time. Alternatively, we can observe that the control U does not affect the revenue directly, but only through soil moisture. Based on this idea, we decompose the optimization problem into two. First, by finding the optimal soil moisture that maximizes revenue, and later finding the control that minimizes the deviation of the optimal soil moisture and the control cost. Consider auxiliary problem 1, where the state process X is defined by the growth yield and the market price process. A control M is admissible if it is adapted to the filtration, satisfies the control constraints, and is a Markovian control over the time horizon. The goal is to find the optimal soil moisture that maximizes the expected discounted revenue Jm over the random time horizon tau. Since the random duration of the dry season is independent of all stochastic processes, we can obtain this alternative expression of the performance criterion, which allow us to treat the control problem as a fixed horizon instead of an indefinite horizon. For auxiliary problem 1, we obtain the following theorem. If the moisture yield function θg of m has a unique maximum, then the optimal soil moisture is a constant. Let's consider the auxiliary problem 2 with the state process X given by the reservoir, soil moisture, and external inflow with an initial value Xn. The control U satisfies the same admissible control of the original problem. However, the objective function here measures the expected discounted aggregate cost given by the penalty for the deviation from the optimal soil moisture and the control cost over the random time. Quadratic or linear cost can be considered. The goal is to find the optimal flow rate which minimizes tilde J. In what follows, we ignore the seasonal time for simplicity and transform the continuous time problem to a Markov decision process by discretizing time. The state process Y controlled by nu has a transition equation given by ys plus 1 with initial value x0. An admissible control nu is a sequence of decision rules which is adapted to the filtration and satisfy the control constraints. Curly J tilde and curly V are the discrete version of the expected discounted aggregate cost and the value function respectively. To solve the problem using dynamic programming, we first consider how to treat the ruin time. If soil moisture reaches minimum or maximum level, we are ruined and it is considered as absorbing state. Hence, we apply the penalty C hat M of n and has the following properties. It is decreasing in n, 0 at the terminal time, and it is greater than the max of the deviation penalty. Therefore, we modify the deviation penalty and define C tilde M of M and N. By applying the method of dynamic programming, we obtain the following recursive equation with terminal value 0. Furthermore, by discretizing the state, the expectation of the recursive equation is approximated below. We present numerical solution of the Markov decision process of the cost minimization problem. Again, for simplicity, we consider the external inflow to be 0. The maximum and the minimum flow rate are indicated by the red and blue color respectively for the control. With the terminal time set at 150 days and allowing for a large cost control, water is pumped at the maximum flow rate for low soil moisture level and gradually decreases towards the optimal soil moisture. Above the optimal soil moisture, no water is pumped. On the other hand, the value function decreases towards 0 as time approaches the terminal time t. The next steps of my work are first completely incorporating uncertain duration of the dry season. Secondly, we will solve the original problem with the 5-dimensional state in discrete time. The challenge here is the backward recursion suffers from the curse of dimensionality, and hence we intend to apply the method of approximate dynamic programming. Afterwards, we'll compare the solution of the original problem and the decomposed auxiliary problems. Thank you very much for watching, and you can find more on the talk using the link below.